Alright, so what I did for my second semester Chem Matters project was the chemistry of the triode. If you have no idea what a triode is, then, well, first of all, you're going to learn, but second of all, it's basically just an incandescent light bulb with some extra electrodes added inside the glass tube to allow amplification of electronic signals. What they used this for was in the early days of radio. They used it to amplify radio signals and basically any other audio or video or electronic signal or whatever. Anything that needed amplification, this is what they used. I chose this because I like history and I like radio and the golden age of radio, and it just appeals to me as like how such a simple idea could like be so useful and that kind of stuff. Alright, to start this out, I'm going to be going over just basics on how like electrical current operates. So AC current, or alternating current, varies direction, or the direction that the electrons flow in a wire at a certain rate per second, measured in hertz. In the USA, the electricity that we get from the wall is 60 hertz at around 120 volts, so it goes back and forth 60 times in 1 second. DC voltage is just a voltage in a straight line in one direction, unchanging. This is what you get from like batteries or the 12-volt port in a car or stuff like that. And then varying DC is once again traveling in one line, but its voltage is changing. One example of all three of these is, or all three of these here is, say, an AM radio broadcast. The carrier wave, or the wave that carries the audio signal, is, say, for AM 550, 550 kilohertz, or 550,000 times a second it goes back and forth. When it does this, they're modulating the voltage corresponding to the waveform of somebody talking, or music, or whatever you want. When it comes to the radio, they tune into that signal at that frequency, then they chop off the bottom half through a process called rectification, so then you have this changing DC current riding on top of the AC waveform at 550 kilohertz, and then they get rid of the carrier wave, so you're left with this changing DC current that you can run through, say, a speaker or headphones or an amplifier or whatever. So a triode basically evolved from a diode, and if you don't know what a diode is, it basically lets electrical current flow in only one direction. The advantage to this is that in, say, a radio receiver, where there's an oscillating current, the carrier wave, which is an AC current like 550 kilohertz, is a radio station. That means that 550,000 times a second, there's a waveform going through the air, like that. What a diode allows you to do is cut that in half and play it through, say, an earphone. Because if you didn't, then each of these phases would cancel each other out, and you would actually hear nothing. But if you use a diode and cut off half of that, then you have something where it can create vibrations and sound. Originally, what they used for diodes was this here. This is a point contact, what they called a cat's whisker diode, because this little piece of metal right here coming into this semiconductor, galena, it looks like a cat's whisker almost. Then along comes the triode. And what the triode allows you to do is flow current from one direction to the other, but it adds a third electrode right here, and that allows you to vary that current. The practical purpose of this is amplification, or switching. Previously, for switching, what they had to do was use a relay down here, where they would have their voltage coming in, and then they would have some wires hooked up to an electromagnet. Whenever the voltage that wanted to be amplified came into here, it would pull this lever closed, completing the circuit between here. Whenever the electromagnet was turned off, this spring pulled it back and completed the circuit up this way. The drawback of these is that they can only function up to about 300 hertz or 300 times a second. They can switch on and off like this, which is obviously not at all useful for like audio amplification. And tubes themselves, for the evacuated tubes part, they evolved from basically Edison's light bulb, which had just simply a heater or a filament to create light rather than heat. And as I said earlier, adding the grid, which is this wavy thing in between here, allows you to vary the current between each of the anode, between the anode and the electrode, or the anode and the cathode, sorry. Electricity will flow from one end to the other, because one is positively charged and one is negatively charged, meaning one has a surplus of electrons and one has a deficit of electrons. And so in the process of flowing between those two spots, in this enclosed vacuum here, applying a voltage to the grid allows you to restrict the flow of some of those electrons, because electrons have like charges, and the more you have in the grid, the more restriction you impose upon the electrons flying from one end to the other inside this vacuum. The way that they get the electrons to fly from the anode to the cathode, or sorry, the cathode to the anode, is by a filament. This, like I said, vacuum tubes evolved from light bulbs, which had just a single filament in them, originally used to create light. But anybody who's seen an incandescent light bulb or touched one after it's been turned on knows that they also create a whole lot of heat. The practical use of this is that when you add two more electrodes in here, say an anode up here and a cathode right here, and you apply electricity to the cathode, then that heats up the cathode and allows the surplus of electrons in there to fly upward, or whatever direction, to the anode. In a old tube TV, they call them tube because it uses a cathode ray tube. It's basically like a really fancy vacuum tube. In the back you have this filament that heats up the cathode. The cathode then, as I read in a book once, quote-unquote, boils off the electrons. You have your grid here to control your brightness in, say, a black and white TV. It focuses those electrons into a beam, deflects the electrons vertically, and then deflects them horizontally, so that you have a single beam which can be drawn anywhere on the surface of the screen. When these electrons come and strike this front of the screen, which is coated with phosphor, it glows. And basically that's the rundown of how a black and white TV works, is that they come up, strike the phosphor, and create light. Then this beam just sweeps across the screen, drawing up the image. And then all the electrons that are left out here, they just get pulled up to the anode on the top and the bottom of the tube, and then are recycled through the whole system. Alright, like I said before, like charges of the electrons repel. So when they are flying out of the cathode and over to the anode, if you add some in between, that blocks them from flying past the grid. So the more voltage you have on the grid, the less voltage you're going to get on the plate or the anode. So if you, say, ran a waveform, like before, a waveform like this through it, you would actually get for an amplified waveform, an inverse of it. So it would be going up and down like that as an inverse of it, because of how if you add electricity here, you get less up here, and if you have less here, then you get more on the anode, which is the inversion here. What you do is you apply an AC current, like I said, to the grid, and this was used in radio receivers for, well, the technical term is the heterodyne receiver, where they would take the high-frequency radio signal and step it down gradually to a lower signal that could be applied to the tube, and then when it's ran through the tube, you rectify it with the diode, or with another tube without a grid, known as a, well, tube diode, basically. Then you run it up to a speaker, and then you get radio. And it acts like an electronic switch, basically. What they did after they first invented the triode was to add more grids. The practical use of this is to do more things with one tube without having to have multiple tubes, which were costly, really pretty costly at the time. First they came up with the tetrode. Tetro, or tet means 4, because there's really 4 electrodes, the cathode, grid, and the anode, and the pentode, which means 5, because there's the cathode, grid, and the anode. They used this for either multiple amplifiers in one tube, or as oscillators, which basically just create an AC waveform, or they could do both, or just a whole bunch of stuff with it. And it increased the compactness and the amount of power required too, which was a big thing. When I was researching all this stuff, I stumbled upon this website here. I guess whoop. And basically what this guy did was, he didn't use a vacuum tube. Instead, he used an ionizing flame. And what this right here is his diode picture, where he took just this steel spring, stuck it in a flame, applied current to this end, and put the cathode just outside of the flame, and was able to achieve rectification, so that electricity only flowed from this side to this side. And then after that, what he did was he added this little grid right here in between, and that allowed him actually to create a very primitive triode. Here, let's see if I can pull this up, this website. And he has a whole big write-up on it. He has some waveforms here that he made on an oscilloscope. There's his diode part, his triode part, a little bit on what gain he was able to achieve with it, an oscillator vacuum tube, or oscillator triode that he built, and there's a waveform that he created, and yeah, just a whole bunch of project stuff with that. And I actually mailed him a letter, because he didn't have his email address, but luckily he was an amateur radio operator, so I looked up his call sign and sent him a letter in the mail, asking him some of the questions that he maybe left a bit vague on that write-up, and he responded back with the answers to those questions, and with that information I conducted just a simple experiment to create a, I didn't do a triode, but I did a very simple diode one, where I had this multimeter hooked up in line with a 9-volt battery down here, which was my bias voltage, my anode here, which was a coat hanger with the end sanded off, and my cathode here, which was just the other end of the multimeter, and then I set them each into the flame of a propane torch, and it was really low voltage that I was able to get through it, but it did prove that electricity will flow through an ionized air source, which is this flame. The flame ionizes the air around it. Yeah, if you didn't know, a flame is actually like air in its plasma state rather than gaseous state. It's a superheated gas. And right here, this was about 3.5 inches between the two, and it was that's a bad picture because it was really a lot higher voltages than that, but I was kind of holding my phone above it too to get a picture. But I was surprised at just how far electricity would travel through there and still produce like a high voltage. And the peak voltage that I got was around 0.7 volts out of a 9 volt, so you're actually like losing electricity as this is acting like a big resistor, but it still does conduct electricity. The last thing that I have on this is because like almost nobody has heard of vacuum tubes these days or knows what they were used for. Nowadays they've been mostly replaced by transistors, and even transistors now have been replaced by integrated circuits, which are basically just thousands or if not millions of transistors on a little tiny piece of silicon the size of your fingernail. What they did with silicon diodes, they were invented in 1947 in Bell Labs, I believe. They took different enough with that. They took different pieces of silicon and did what they call doping, where they treat it with different chemicals to create a different kind of semiconductor property. Then they put these all in series with each other. They called them P-channel and N-channel doped pieces of silicon. And a PNP transistor, this is a standard PNP transistor, and this is a standard NPN transistor. Basically just changes the direction in which current will flow through it, but the practical use of that is that it acts as a semiconductor switch, and it uses a whole lot less electricity because you don't have a heater for it, and it doesn't require as much electricity anyway to travel through that vacuum. And then those, of course, were put into place in first probably the pocket radios in the early 50s, and then in the early 60s that evolved into the first integrated circuits, and from there into logic circuits, and then eventually into the early 1970s microprocessors, which are now what powers everything, like from our phones in our pocket to computers to cars, everything. And all that started with just a simple need to amplify radio signals. So yeah, I hope this was informative and stuff, and yeah, thanks.